Today on the sixth lecture, let us discuss about Earth's hydrologic system. The moment we talk about hydrologic system, we are talking about the water and its cycling in three different phases. We have availability of water in liquid, solid and the gaseous formation. So, let us see how it cycles around around all these three spheres and across all these three phases, and discuss a bit of overview as far as the hydrologic cycle of Earth is concerned. And these are the concepts we are going to discuss today. First is water cycle or water balance. Then we will also discuss about transpiration, the budgets as far as water budget is concerned and energy budget is concerned in terms of water cycling, and then the evapotranspiration, which is a combination of evaporation and transpiration, and we will have a look at a case study that discusses on hydrological balance as far as the land use and land cover change is concerned. So, this will explain us how the three processes, particularly the evapotranspiration, the base flow, the surface runoff, all these are guided or regulated or hampered by any change in terms of land use and land cover over our surfaces. So, this will discuss as a case study example with respect to a river basin. So, the first one is about the storage. Friends, we all know the storage as far as the total Earth, if you put as 100% of the water, out of that 97.4% are there in the ocean. So, the leftover 2.6%, out of 2.6%, 2% are again logged in ice caps and glaciers, whereas only 0.58% is available in groundwater. So, next 0.02, 0.004% of water are available in lake and rivers and the soil water. Rest about 0.001% are available in the atmosphere in terms of the moisture or gases. So, let us see. So, this is a broad idea that how the water is stored or distributed over different pools on our surfaces. 97.4 so is in the ocean. So, let us see out of this 100% budget, if we put it in terms of a quantitative term, the oceans contain about 1,335 lakhs 40,000 square kilometer cube of water. So, this is the amount which is budgeted as far as the water content as far as the ocean is concerned. So, then this ocean is, that means the water in ocean has been dealt separately than that of the terrestrial water. So, through the process of evaporation, ocean loses about 13,000 kilometer cube of water per year, whereas again through the process of precipitation in the same year or per year, it again gives back about 373,000 kilometer cube of water. So, rest deficit of 40,000 kilometer cube of water are explained by the process of transport. So, let us have a look at the terrestrial water cycling. So, as far as the terrestrial water cycling is concerned, the terrestrial domain, the Earth's terrestrial landmass receives about 113,000 kilometer cube of water per year, out of which 73,000 kilometer cube of water is again goes back in terms of evaporation, and rest about 40,000 is going as runoff, 40,000 kilometer cube as going as runoff, that again goes back to or added to finally to the ocean. So, that balances the evaporation plus this runoff, the precipitation plus this runoff, that balances the oceanic evaporation term, that is 413,000 kilometer cube per year. And coming to the right hand side figure, ice, which contains about 2% of the total water as far as the budget is concerned, 372,000 kilometer cube of ice means of water is frozen or is deposited in form of the ice or the glaciers, whereas the land contains about 15,600,000 kilometer cube of water in form of sweet water, in form of any other formations or the groundwater formations. So, this is in terms of quantitative term, and broadly what the take from this particular slide is the evaporation is balanced by the oceanic evaporation is balanced by precipitation it receives and the runoff it receives from the terrestrial rainfall or precipitation, whereas the terrestrial is balanced by the precipitation, the transport term and the evaporation, and the ice and land means holds lot of water, those are the sweet water. So, ocean, in terms of ocean, evaporation exceeds precipitation. So, in a sense there is in this sense there is water deficit as far as ocean sphere is concerned. The land, the precipitation exceeds evapotranspiration because you have a surplus in as far as the runoff is concerned. So, this runoff returns to the oceans, maintaining Earth's water balance. Now, let us look at the water cycle term as far as addition of the two components, importantly the vegetation parameter and also the percolation parameter through this, and the transpiration, percolation, all these terms. Let us have a look at this. So, water cycle, so that is a kind of continuous movement of water above and below the earth's surface. So, this is driven by solar energy and gravity, that is the important point. And the significance of this of the water cycle is it provides fresh water to support particularly the terrestrial ecosystems. If the cycling is not there, where the water will come. So, this actually supplies, this water cycle supplies continuously supply fresh water availability to the terrestrial ecosystems, and in this course it purifies and recycles the water, and thereby it maintains the groundwater and surface water flow. So, now let us see the water evaporates in terms of which is represented in terms of E, and also transpires. So, transpiration, evaporation and evapotranspiration. So, E plus T is ET, evaporation plus transpiration. So, evaporation means it is the loss of water in form of water vapor, and if it is from a vegetation surface through the leaf stomata, then it is transpiration, and from rest of the surfaces it is evaporation, but it is precisely the loss of water in form of water vapor. So, water rises, cools and condenses as clouds, and the clouds precipitate, then water is stored in time and the excess is run off as stream flow, and some of them also infiltrates. So, we say infiltration happens. So, again you have percolation represented by the term Pc to recharge the groundwater. So, water returns to air, and similarly, and in this course the cycle gets repeated. The figure itself talks about the graphic representation in terms of percolation. So, the left hand side represented by Pc, that is actually contributing to the groundwater recharge, the evaporation, and then Q is the overland flow, or you say sometime the stream flow. and the plants, they lose water in the process of transpiration. In fact, we all understand that to a photosynthesis to happen, it has to lose water in form of water vapor through the same pore called stomata. So, you have stomatal transpiration done by the plants, the plant system, and then there is also some loss in terms of evaporation from the terrestrial lakes, and also the evaporation and interception. So, what is interception? You have a canopy, you have a tree, you have a canopy. The incoming rainfall actually is being intercepted by this canopy. So, some is thoroughfall. That means it is not intercepted by the plant canopy, and many of them where you have a system, a plant system or a vegetation system is there, you have an interception. So, interception actually allows little lag in terms of that particular precipitation to reach to the ground or to the soil or the base. Now, moving on towards the evapotranspiration, and particularly the term transpiration, how it is a specialized form of water loss in form of water vapor from the leaf surfaces. Friends, the left hand depiction talks about the interception evaporation and the transpiration. On the left hand side, you can see the microscopic view of stomata. As all of us know, most of the mesophyll cells, the plants, the mesophyll cells and the lower surface, they have lot of stomata. The stomata have the guard cells which controls their opening and closing. So, the opening means it allows gaseous exchange, it allows exchange of carbon and water and other gases. But here we are concerned about the water flow or the water exchange through the stomatal pore. So, what does it mean by water? So, by this transpiration, what happens if you see the right hand side, a plant system maintains a kind of SPAC, soil plant atmosphere continuum along a water potential, and here their water potential in terms of MPa is given, that is at soil it is minus 0.01, then it is at root it is minus 0.1, then in terms of leaves it is just 0.1, and there at air it is 100 MPa. So, in this what happens? That means you have a quench, you have a gradient in terms of deficit, or the water to be pulled from the soil through root to the leaf and finally to the outer air or outer atmosphere. So, it is a force, or you say a kind of water, a kind of vapor pressure deficit is maintained, so that you have a quench and the water is pulled from the soil up to the leaf, and then there a phase change happens, and you have it changes its phase from liquid water to a gaseous form and escapes out through the stomatal pore, which is present on the leaf surfaces, dominantly on the lower side of the leaf surfaces, to the outer atmosphere. So, this process is explained in terms along a water potential, which acts as a gradient in terms of vapor pressure deficit, and which pulls the water from the soil up to the outer atmosphere through stomatal pores. And this stomata is the main interface as far as the exchange of this water vapor is concerned between the leaf surface and the surrounding air. So, through this the water loss we discuss under the framework of transpiration. On the right hand side of this figure, there is the interception evaporation. look there, the depiction says that yes, you have some amount of bubbles or some amount of water particles, water bubbles, they remain attached, or they remain, what you say, in terms of a adsorption and absorption mode on the leaf surfaces, and this means few fates. It also can be evaporated from then and there, or some of them also pulse and go to as a surface recharge or surface runoff. So these are the two fates the plant system meets as far as the water exchange is concerned. So evapotranspiration is equal to evaporation plus plant transpiration plus the interception evaporation. So precisely the liquid water gets converted to vapor water, the earth surface and plants interface with the atmosphere. It is driven by the radiation, particularly the solar radiation, the temperature and the vapor pressure deficit, and controlled by many things including the leaf area index, of course the carbon dioxide concentration, which we actually discuss in terms of photosynthesis, because the same pore, the stomata, acts as a interface place as far as the CO2 and carbon dioxide, CO2 and water vapor, as far as the process of photosynthesis and transpiration is concerned. Sometimes we discuss it as a compromise process, the photosynthesis and transpiration. That means through the same pore, if carbon dioxide is coming in from the atmosphere inside the plant surface through this pore, at the same time the water vapor has to go out from inside the leaf surface to the outer atmosphere. So that is why we understand this in terms of the leaf area index, the carbon dioxide and also the soil moisture. Yes, so understanding this actually provides us a background to understand how different types of climate risks will be involved if some alteration in terms of this plant system is concerned, in terms of deforestation, which is contributing to this in negatively, and afforestation, which will contribute to positively as far as the climate is concerned. So next, let us understand the water balance. So in terms of balance, we will discuss about two. One is water, another is energy. So in terms of the water balance, we discuss the inflow, outflow and the storage catchment. So what happens in a hydrological system, we always talk about a system in terms of a water set, in terms of a catchment. What does a catchment means? That means it is an unit area which accumulates the incoming precipitation that includes rainfall, snowfall and other things. So in a system, in a hydrological unit or a water shed or a catchment, the income as far as the precipitation is there has to be balanced with respect to whatever is outflow. So here if you see the potential ET, the actual ET, and let us talk about the soil water storage. The soil water storage, which storage capacity, which is a kind of net groundwater flow out, that is represented by the term G, and the different terms have been depicted there, potentiality and actuality. So you have different conditions that regulate or that controls the evapotranspiration, and that is why the actual ET is different or differs from the potential. Potential is maximum how is possible, but in actual way it may be little less, always depending on many or various environmental constraints. Coming to the temperature and precipitation, snow melt, snow storage, rain and direct rainfall, which is represented by the term Q. So let us look at the right hand side, the water budget equation for a catchment for a time interval. P is equal to E, that is the evapotranspiration, T evaporation, T is the transpiration, T term here is and the Q is the direct runoff, and delta S, this S term is for the storage or the surface this, and the G is for the soil water storage, and delta S term is for the runoff term, direct term, and this is also the storage change. Yes, the importance, it particularly the water balance, understanding the water budget, it helps in understanding the hydrological and climatical influences on this, and thereby you can manage the water and the irrigation. It predicts the droughts and floods, ensures sustainable groundwater utilization. So, delta S, that is the change in storage, and S is the total storage, and that is the water stored on surface plus groundwater plus the soil moisture. So, what is the take home from this particular slide is, yes, the water budget can be studied in terms of the catchment water balance equations that takes care of inflow, outflow, and the storage. Now, let us move on to the next one, that is the energy budget. As far as the energy budget method is concerned, we can see the delta E, which represents the energy needed to change the phase of water from liquid to gas. Rn is represented by the net radiation, G is the soil heat flux, and H is the sensible heat flux. So, at a diurnal variation of the components of the energy that balance above a well water transferring surface on a cloudless day. So, on the x axis at a diurnal scale, the in terms of hour has been shown, and on the y axis energy arriving or leaving the surface. It is shown over a well water transferring surface. That means you have a vegetation or a good agricultural land or a forest land, right. So, then let us see the G there. It is showing that the soil heat flux is slightly higher during the midday or around 12 noon, whereas the H, that is the sensible heat flux, increases at about 5 or 6 a.m. and attains its peak again post noon about 12:30 or during that time, and again it attains its minima post dusk or post evening around 6 or 6 p.m. and then you have the delta E, that is the energy needed to change the phase of the water, and the solar radiation. So, this all needs to be balanced. So, that is why the equation is delta E is equal to Rn plus G minus the H. So, this talks about the water budget method as far as the calculation goes, as any catchment or any watershed is concerned, and this particular depiction is more suitable for a well water transferring surface. That means it should be having vegetation. Now, let us move on to the equation in a different context. You have a depiction that shows the watershed or the catchment. So, on this side ES is the energy stored in terms of the energy stored in a system, particularly in a catchment, which is or you say it can be represented with this unit G calorie and centimeter square per day, is equal to EA minus RT, and EA is the net energy advected, that is the net energy content of incoming and outgoing water, plus the RT, that is the total solar radiation, minus RR, which is the reflected solar radiation, plus EE, that is the energy used for evaporation, or you say the latent heat, plus Hn, as we understood previous slide, is sensible heat loss from the water body to the atmosphere, and R1 we say RL, that we say the net long wave radiation exchange between atmosphere and the water body. So, this R1 or RL includes the long wave radiation from the atmosphere, reflected LW radiation and LW radiation emitted or longer wavelength radiation emitted by the water. So, with this understanding, let us get into the what you say relational mode. What do you mean by the relational mode? We have a given land surface. The land surface, you have vegetation, you have water body, you have a barren land, you have agricultural land, and many others. And in this era or in this domain, we are regularly altering, we are regularly converting one land use to other, one land cover to other. We are going for cultivation, so we are changing it from barren land to a cultivation land. We are going for deforestation, burning, and bringing a forest land back to a barren land. So, lot of this is happening. So, we did a study, the Das et al., and it is published in 2018, and from there this particular example has been picked as a case study for our understanding. What we did, on the left hand side, upper lower AI and AII, the left hand side two figures talks about the loss and gain of these 5 different categories of the land use cover. So, what are the 5 different categories? They are the mixed forest, the built-ups, the scrublands, the croplands, and deciduous broad-leaved forests. So, these 5 forest types have been taken, these 5 land use land cover classes were taken for this Mahanadi river basin, and the change between 2005 and 25 has been calculated there. And then the corroborative middle one, that means BI and II, is the BI talks about the runoff, and the II, that means the lower middle, talks about the change in the base flow, and the upper right talks about the change in the evapotranspiration. And friends, if you corroborate with the change in the land use land cover, it actually gives an impression that how, because of the change in land use land cover, there are changes in all these three different components of the hydrological processes, that is the ET, runoff, and base flow. So, that means what is the lesson from here, from this case study is, yes, different land use land cover units have different runoff, base flow, and ET characteristics. Any alteration or any change in this land use land cover will have corroborative changes or effect in terms of the runoff, ET or evapotranspiration, and the base flow. So, these studies are really important and realistic, and the land use land cover which is taken from remote sensing data is also a very important data source to support these kind of studies, and gives us impression that how, because of our alterations in land use land cover, the hydrological system is getting impacted and affected, and this informs us as a policymaker to take appropriate policy or management decision to restore or to have a balance as far as the hydrology is concerned. These two references have been used, particularly the book by Gordon Bonan, and this particular publication from our team has been taken as an for this particular class. And then these are the conclusions. I will read it out what we discussed now. The water cycle is the continuous movement of water on, above, and below Earth's surface, driven by solar energy and gravity. It includes key processes like evapotranspiration, precipitation, runoff, and groundwater flow, which together regulate water and energy transfer. The water budget equation given by this expression ensures the balance between input and output in a catchment. So, globally about 96.5% of the water that is saline is in ocean, and only 2.5 or 2.6% is there available as in terms of fresh water. Water balance maintains climate stability and ecosystem health. That is why we discuss this, because water balance maintains the climate stability. Any changes, any alteration will have a risk as far as climate is concerned. That is why we will again discuss this in terms of climate risks. So, models like SWOT, BIG help in assessing the water vulnerability, predicting the flood risks, seasonal changes in water flow, changes in the hydrological variables as we discussed in terms of a case study taking the land use, land cover change. So, in this today's lecture number 6, we discussed about the hydrological system, the cycling of water between the ocean, atmosphere and the terrestrial surfaces, how it cycles across 3 different phases, liquid, water, liquid, solid and the gaseous stages. And also the 2 formations in terms of loss of water was discussed as evaporation and transpiration. Transpiration from the vegetation surface, and from non-vegetation surface it is the evaporation, and together in totality we discussed it in terms of evapotranspiration. So, friends, try to understand this in terms of water balance budget or energy balance budget as far as any hydrological unit or watershed is concerned. Sometimes we go up to the larger unit, that is the river basin as the catchment. Thank you very much for your patience listening and being here. Thank you very much.